Greetings YouTubers, I'm Rick the Tech Enthusiast here with the next Elegoo lesson number 20, Sound Sensor Module. In this lesson, we'll check out the sound sensor module that's provided with the Elegoo kit. We'll build and configure a simple circuit that's provided in the tutorial to demonstrate the functionality. Then we'll build a custom sound sensor calibrator and LED switch. So let's start building. The sound sensor module that is included in the kit provides both a digital triggered and analog output. The provided datasheet indicates that this module is a KY-037. However, after a little researching, I found that the Keys KY-037 is a 3-prong module with only a digital output. The KY-038 sound sensor module has both an analog and digital output. So it seems that the provided datasheet might be slightly incorrect. The datasheet includes the module pinout and some sample code, but that's about it. I did find this schematic online, and I made a couple of corrections, that gives us a better idea of what's happening in the module. First, we can easily see that the LED 1 turns on when the power is applied. Next, we see that the second LM393 comparator drives LED number 2. Now let's focus on the left-hand side of the circuit. The electret condenser microphone sends a sinusoidal voltage signal to the first LM393 comparator. Note the polarity. If the signal is greater than the voltage divider, 2.5 volts, then the first comparator switches low, and that's what is sent to the D0 pin. That output is also sent to the second comparator's negative input, causing it to switch high and turning off the LED number 2. If the signal is less than the voltage divider, the first comparator's output switches high and the second comparator's switches low, turning on LED number 2. The potentiometer is adjusted to obtain the desired sensitivity, or rather the initial DC bias level, and is where we get the analog A0 signal output. What's important to note is that the D0 output has little to do with frequency. It is simply triggered by a loud enough sound to overcome the comparator, and the analog output is not amplified. The potentiometer simply applies a DC bias level to the analog signal. It is also important to consider how you adjust the DC bias level. If you adjust it so that LED number 2 remains off, note that D0 will be normally low and only momentarily switches high when a sound triggers the device. If you adjust it so that LED number 2 remains on, D0 is normally high and only momentarily switches low when the sound triggers the device. To make the sensor work, the potentiometer needs to be adjusted by turning the tiny screw head counterclockwise until LED number 2 turns off. Now if you want D0 to be normally low, slowly turn it clockwise and then back counterclockwise super slowly until LED number 2 just turns off. LED 2 will flash on when D0 goes high. It may take several attempts to get it just right. If you want D0 to be normally high, repeat the steps before, but carefully adjust the potentiometer until LED number 2 just turns on. LED number 2 will flash off when D0 goes low. Unfortunately, the datasheet contains very little information, and the tutorial goes into great detail about the microphone, so it might be an interesting read, but it doesn't cover the sensor much. For this lesson, we'll need the following items from your kit: the Elegoo Arduino UNO R3 board, the sound sensor module, aka KY-037, or rather the KY-038 module, 4 female to male jumper wires. On page 143, you'll see the following schematic, which is completely wrong. The internal KY-038 schematic looks nothing like this. However, Here's a revised schematic. I made another attempt at creating, or rather modifying, an existing fritzing component to make a new component for the KY-038 module. A jumper connects the A0 output pin of the sensor to the Arduino's A0 pin. Another jumper connects between the D0 to D3. Then they're just power and ground. Simple. On page 144, you'll see the wiring diagram, with a photo on page 145. And here's my newly created fritzing Elegoo UNO R3 board and the KY-038 module. Note we're not going to be using the breadboard. We're going to directly connect the jumpers between the Arduino and the sound sensor. Okay, let's jump to the code. As before, we'll load the recommended sketch provided in the tutorial. Go to the File menu item, select Open, and browse to where you saved the Elegoo files. Then under your language, Code, under Lesson 20 Sound Sensor Module, and oh, this time there are two choices: analog signal output and digital signal output. We'll start with the digital signal output and open the digital signal output.ino file. Looking at the code, you'll see it starts off by defining a couple of integers for the LED and the button pin. That's interesting. Followed by an integer val. Oops, I think the semicolon is a mistake. Let's just delete that. The void setup sets the pin modes for the LED pin and button pin to output and input. The void loop, okay, one moment as I tidy up a few things and make this a little bit more readable. That's better. The void loop starts with a digital read of the button pin and sets it to the val. This is followed by an if statement that checks if val is high. If so, perform a digital write to the LED as high, else a digital write to the LED as low. That's simple. Let's upload the code and try it out. Okay, here we are with the digital signal output sketch installed. And you can see here we have the Elegoo, and there's D0 hooking up to, D3 hooking up to D0 here, and A0 hooking up to A0 over here. And then there's power and ground. And then to test out the microphone, let's just tap on the table here. And you can just see right there is the LED pin that will flash on off, as well as this LED pin whenever there's a sound. Pretty simple but effective. Okay, let's try the analog version. This time, load up the sketch from the analog signal output, analog signal output.ino file. Like before, it defines the integers for the sensor pin and LED pin, followed by an integer sensor value and setting it to 0. The void setup sets the pin mode for the LED pin and starts the serial port. The void loop, just a second. Okay, that's better. The void loop starts with an analog read of the sensor pin. Then it turns on the LED. It has a delay with a sensor value. Then it turns off the LED, and then it has another delay with that same value. Then it finally sends that value to the serial port. I'm not sure how valuable this sketch is, but let's upload the code and try it out. Alrighty, we have the code uploaded. Let's see what we get here. Let's try a little tap. Seems to be just flashing the LED back and forth. Let me try something else. Let me blow on it. There's some small changes in the digital write for the LED and the analog read values, but it seemed to hover around 515 or so. Again, not sure how useful this sketch is. Well, the previous sketches show some basic functionality. Let's make a new circuit to toggle on and off an external LED and also provide a real-time analog voltage value. So I've come up with this sound sensor circuit and sketched to better illustrate the module's functionality. Originally, I wanted to do a decibel meter, but after researching the idea, I wasn't convinced that the DC biased analog values could reliably be converted to a sound pressure logarithmic scale to measure decibels. Anyhow, let's check out the schematic. The schematic is simple. The sound sensor is connected like before to the A0 and the D3 pins, and of course the 5 volts and ground. An OLED display is connected to pins 13, 11, 8, 7, and 6, and an external LED is connected to pin 5 through a 330 ohm resistor. Looking at the wiring diagram, you can see that the resistor, LED, and the OLED display are mounted to the breadboard. The sound sensor will also be mounted to the breadboard, but is shown this way for clarity. The sketch begins with an include U8G2 lib.h library, which is followed by several hardware constants like the OLED pins, a statement to instantiate the U8G2 class as an OLED object, the LED pin, digital pin, and analog pin. Then I include some global constants used in the sketch for a couple of different fonts, OLED screen size, the sketch title as a char array, length of this array, and delay time, which is used to set the minimum time period that the LED stays on or off. I use the define large font and main font here so that the fonts can be easily changed in just one place. The list of fonts for the U8G2 library can be found at this website. This is followed by a few global variables to track time, the LED state, and the font row heights, since I'm planning on using the 2 different font sizes. The void setup begins by starting the serial monitor. Next, pin modes are defined for the LED as output and digital pin as input. Then we begin the OLED display object. Clear the screen, set the bitmap mode and the draw color. Then, since I'm using 2 different font sizes, the sketch calculates the row height by calling getAscent and getDescent, which returns the maximum height above and below the font's baseline. These are added together with an additional pixel height to give the 2 different row heights. Next is the display title, and we set the first row position or the Y coordinate. The for loop loops through the sketch title array, each time calculating the column position so that each word is centered on the screen. The set cursor moves the cursor to the required position, and the OLED print sends the word to the buffer, incrementing the row position after each word. Finally, the send buffer and a small delay are called, which should show the sketch title for 2 seconds. The void loop is super simple. It runs the check analog and then the check digital functions, and then it loops. The void check analog function begins with several local variables, two of them as static. The static values are remembered each time the function is called, so they're kind of like a global variable, but only accessible by the local function. My thought process was to limit the number of global variables wherever I could, or move variables that are used only by a single function as a local variable. I'm still working on it. Then there's the integer variable a value to store the analog value, float variables to track the current, maximum, and minimum voltage values. Finally, an analog read from the analog pin to set the A value. Next, the minimum and maximum analog values are set if the new value is less than or greater than the existing values. The volts, min volts, and max volts are calculated. We'll skip the serial debug code. And finally, it calls the draw meter function, passing the calculated values and a char v for the unit. The draw meter function does all the OLED display work. Originally, this was part of the check analog function, but it became kind of cluttered, and I thought it would make it more reusable as a separate piece of code. Anyhow, I tried to make this more general for different display sizes and maybe even different past values. It starts with the local variable to handle columns and row positions, a string length that I'll explain later, and a char array. The sketch continues to a series of other variables that determines what size the gauge or meter on the screen will be. Again, I was trying to make it generic. Hopefully, it should accommodate different size screens. By simply adjusting the screen width or screen height global variables, most of these values should auto-adjust. Meter height must be manually adjusted. Okay, the next OLED buffer is cleared, which clears the display. Working on the assumption that the float value sizes are unknown, and that the unit value, in this case V, needs to be added to the float value, the float value needs to be converted to a char array. This is done by first determining how many digits the float has. This starts by getting just the integer value of the float and setting it to the I value. Then dividing the I value by 10 repeatedly until the I value is 0, each time incrementing the string length. Then to accommodate the period and the two decimal values, we simply add 3 to the string length. The D to strf, or double to string function, converts the float to a char array using the string length value and 2 for the number of decimal places. Then to add the char v unit value, we use the sprintf method. It requires the array to store the resulting string, or char array, the format which also identifies the parameter types, like in this case, the %s for string and the %c for char, and any additional string values, like in this case, a space. Now we're ready to display the main value. I chose to use the large font here. Then the column position is calculated using the screen width and subtracting the char array width by calling the U8G2's getStringWidth method, and then dividing that value by 2 to determine the column starting point. The row position uses the predetermined large font row height. Since the row height includes an extra pixel, I subtract 1 from the row height value to position the char array top center. I should point out that the getStringWidth method is particular and is why all the extra steps were needed. Next comes the minimum and maximum values and their associated tick marks. The minimum voltage value is displayed using the main font. positioning it to the left of the next row with the 4-pixel buffer. Set cursor moves the cursor. OLED print prints the float without having to convert it to a char array or a string. The minimum tick mark is drawn by first determining the column position using a map function. Since the value is a float and has 2 decimal places, I multiplied the value by 100 and then use a range from 0 to 500. To where the meter will start, to the meter width plus meter start. Yep, there's a lot more to be done to make this autodynamic, but it's a good start. The draw line is positioned above the meter and the other tick marks using the value min-max tick mark length. The max voltage requires that it be converted to a char array to use the getStringWidth method to position the value to the right. Otherwise, the max value and the max tick marks are displayed in a similar manner. Drawing the voltmeter is done in 4 steps. The major tick marks are drawn using the major tick spacing value in a for loop. The minor tick marks are done the same way using the minor tick mark spacing value. The outline is drawn using a draw R frame method, using the meter size values provided above. The R method allows for a radius value to be included that gives it a kind of a tapered or round shape. Then the bar itself is drawn using the draw R box method after determining the bar length, again using the map function. Finally, we use sendBuffer method to display the meter. The check digital function is simple in comparison. Here I wanted a function to turn on the LED with a loud sound, and then turn off the LED with a loud sound. And to avoid bouncing, I added the delay time, which can be adjusted above. The local variables start with a bool variable d value, which is set to high, and an unsigned long current millis is set to the current Arduino millis time value. Next, a digital read of the digital pin is set to the d value variable. The if statement checks if the current time minus the previous time is greater than the delay time, and if the d value is also low. If both of these are true, the LED state is changed. A digital write then writes the LED state to the LED pin, and the previous millis gets the current millis. Super simple. As you can see, the sketch title is centered and it lasts about 2 seconds. And then we have the large font and the analog voltage with the concatenated unit value V. Over on the left hand side we have the minimum voltage, and on the right hand side we have the maximum voltage. And you see they're so close that their tick marks are right next to each other. Below that we have the major ticks right here, and then the minor ticks going across, and the little bar graph with a little bit of a radius end. Now I thought about using something really loud or clapping really loud, but I thought that'd be terrible on the microphone. So instead I'm going to use this turkey baster. I'm going to blow gently across the microphone to simulate a loud noise. Let's try this. You can see that there was quite of a spike here, a range of minimum and maximum that was read from the microphone, and the new minimum maximum tick marks recorded here, and the LED has turned on and remains on until I blow across or make a loud noise across the microphone. Let's try it again. All right, LED is off. The new minimum and maximum values seems to be working. Let's try one more time. And each time you can see that the bar graph jumps, showing those max and min values. Excellent. I think it works pretty well. Well, that's it for this lesson. I hope you've enjoyed learning a little about the sound sensor module, which should be labeled as a KY-038. If you like this sketch, be sure to let me know in the comments section below. I'll have additional links for other interesting videos and code for this project in the show notes below. Join me next time for Lesson 21, RC522 RFID module. If you like this video, please give it a big thumbs up and don't forget to hit the subscribe button. Thanks and see you next time.